Hey people, let's continue with limits. And I gave you these two questions to solve, like what were the limits of these using infinite series, and I got a lot of answers and they were all correct, so that's good. So now let me solve this one. Okay, so we have here limit x approaches 0 ex minus 1 upon x, and we know that e to the power x infinite series is this one here. So we have 1 plus x by 1 factorial plus x square upon 2 factorial and so on, vagara vagara vagara. So now let's move on here to the question, and we know that e to the power x is 1 plus x over 1 factorial and x square upon 2 factorial and so on. I'm just writing so on because we do not need the higher terms. And then is minus 1, and this is all over x, and there is a limit x approaches 0, right? So 1 and 1 gets cancelled, right? And here we get is equal to x plus x square over 2 factorial plus so on over x, and here we go. So we get 1 x is cancelled, and we get last is 1 plus x 1 plus right 1 plus x upon 2 factorial and so on, and when you put x equal to 0 I get equal to 1. So we have got that this limit is equal to 1. Okay, this limit is equal to 1. Okay, now let's talk about this limit. Now we know that the expansion of this here, this number here, is this x upon 1 minus x square upon 2 plus x upon 3 and so on, so on, so on. So we just write it like that: x minus x square upon 2 plus x cube upon 3 and so on, so on, so on upon x, and there is a limit x approaching 0, and then we write, we cancel x here, we cancel 1x here and so on, we cancel it, thus we are left with 1 minus x by 2 plus x square by 3 and so on till infinity. Thus we now have limit x approaches 0. That means we can put x equal to 0. So that is also equal to 1. So we get that this is also equal to 1. And we notice that both of them are a form of 0 by 0. The 0 by 0 form. Similarly here also it is 0 by 0 form. Right. So we found out limits using infinite series of sin x, tan x, cos x, 1 minus cos x upon x square, 1 minus cos x upon x, e to the power x minus 1 upon x, and ln of 1 plus x upon x. So now we move back to differentiation, and we now have to differentiate certain functions using the first principle. So let us just revise what is the first principle. But the first principle states that the differential of any function like dy by upon dx is limit h approaches 0 f of x plus h minus f of x upon h. So let us solve y equal to x square and find a differential for this function. So let me just solve it for you, and you can solve it side by side, right? So we have been given we need to find dy by dx, and that is equal to limit h approaches 0 f of x plus h. We are finding at any x, right, upon h, right? Okay, so now let's put the values. We have x plus h whole square minus x square upon h, and let us just open the brackets. Or you can do one more thing. Let's apply a square minus b square on this one. So okay, there is a limit h approaches 0 here. Limit h approaches 0, right? So we have equal to limit h approaches 0 to x plus h, and it is x plus h minus x, which will be h upon h, and here we cancel out the h. So what are we left? We are left with limit h approaches 0 to x plus h, and then I put h equal to 0, I get equal to 2x. So you should remember that the differential of x square with respect to x is equal to 2x, and there is a general formula for that too. The general formula is d or dx of x to the power n is equal to n x n minus 1, which can be derived by using the binomial theorem. And let's see, I give you this question for solving. Just send me the solutions of how to get this differential equation using binomial theorem. Now we have y equal to sine x. Let's also, one thing you need to note here when we're using y equal to sine x is that okay, we'll do it afterwards. First we'll do y equal to e to the power x and y equal to ln of x. Now we have a hint there, limit x approaches 0, e to the power x minus 1 upon x is equal to 1, and we have calculated that now only, so we do not need this hint right now, but we surely need to find the differential of this. So we have dy by dx, which will be limit h, that limit h approaches 0, f of x plus h minus f of x over h, right? Now let's just substitute the values. So we have limit x approaches 0. Okay, here it is h approaches 0. Yeah, it is h approaches 0. E to the power x plus h minus e to the power x upon h. Now we write limit h approaches 0, e to the power x common, e to the power h minus 1 over h. And now we know the product rule too, which I told you in the last class. It is we can write limit h approaches 0, e to the power x dot means multiplied by limit h to the power 0, e to the power h minus 1 upon h, and we know that this is equal to 1. So this will be equal to 1, and thus we will get limit h approaches 0, e to the power x into 1, and there is no term of h, so we need not apply, and directly will be equal to e to the power x. So we have found a very interesting result, that the differentiation of e to the power x is e to the power x, which is quite absurd to understand, but it is like that it comes out to be the same. It is a very interesting function in which the differential comes out to be e to the power. Well, it is a very interesting function, we'll discuss about it, and it has a lot of implications too, so we will study about that too. Now let us move on with y equal to ln of x. Now y equal to L is similarly like dy by dx, the first principle, which is equal to limit h approaches 0, f of x plus h minus f of x over h, right? Now let us put the values now. Limit h approaches 0, ln of x plus h minus ln of x over h. Now there is a small point to be noted, that there is a small property of log. Which goes by this, that if there is ln of a plus ln of b, then this is equal to ln of ab. And similarly, if we have ln of a minus ln of b, this will be equal to ln of a by b, which you can prove using what we call that exponential terms, like we can use exponents to prove that thing. So similarly we'll use that thing here also. So I'll write is equal to limit h tends to 0 ln of x plus h over x over h. Then I divide this thing by x and I multiply it by x. So when they cancel they will be equal to 1, so we have no problem in substituting or introducing that. Now I get ln of 1 plus h by x over 1 h by x into 1 by x. Right, we'll get this. So we now see that h is equal to 0 and this thing here is of the form ln of 1 plus x upon x, limit x tends to 0. So we can say this is equal to 1, and using the product rule we can say that, so we will get 1 by x is the derivative. So we need to remember that d by dx of ln of x is equal to 1 by x. So these are just small functions which we need find the differentiation. There are bigger functions too, like trigonometric function, and they require a kind of trigonometric rules, and that will be the next topic. So that is all for today. Kindly revise this, because the finding of differentiation is very important, and we'll move on with us in the next lecture.